right, so I think it's 10:45, so actually let's get started. Hello, everyone. Welcome to today's keynote talk. We are very excited to have Professor Sanjeev Arora as our first keynote speaker. And as we all know, deep learning has been a revolutionizing technology that enables exciting developments in almost all fields, engineering, biology, physics, and so on. And certainly has been also getting a lot of attentions from the symmetrics community. But we all know that compared to its great success, much less has been known about the real source of its magic power. And it remains a critical task for us to understand what's really inside inside deep learning. And Professor Arora is well recognized as one of the leaders towards understanding what's inside this black box and has made fundamental contributions towards establishing a theoretical foundation for deep learning. Professor Arora has received many prestigious awards, including the Packer Fellowship, Simon's Investigator Award. He also received the Gödel Prize twice, one for his seminal PCP theorem, which I assume many of you already know, and the other for his breakthrough approximation algorithm for Euclidean TSP. Professor Arora received the ACM Prize in Computing and the Fulkerson Prize. He's a fellow of AAAS and a member of National Academy of Science. And today he's going to tell us about the exciting results on the recent development of understanding deep learning. And so without further ado, let's welcome Professor Sanjeev Arora.
Thank you very much. It's a pleasure and an honor to speak here. So today's topic is opening the black box of deep learning and hopefully get mathematical understanding. And there's a lot of different threads of research here, some of which I'll include in the talk, and some of the technical ones, maybe you can find other talks of mine online with some of the details. So, yes, I think most scientific audiences know today that deep learning is at the core of artificial intelligence and machine learning in a variety of domains. And the big shift here is that we've gone from programming-based, human-designed methods or algorithms to fitting models to data. And this is also beginning to happen a lot in the sigmetrics community, going from hand-designed models for systems to just fitting models to data. Now, the black box here refers to this black box of deep learning, where you basically are thinking of this multi-layered function, and the input comes in and output comes out, and it's trained in some black box way. And we're trying to gain mathematical understanding of that. So let me first isolate out the conceptual hurdle for doing theory. And I know that there's a lot of overlap between traditional theoretical CS and sigmetrics, including in the talk that was just happening before my talk. So I want to point out the big conceptual hurdle that one has to get over in thinking about modern machine learning. And this has to do with the definition of what's an algorithm that's ingrained in us. And so I looked at a few algorithms textbooks, undergrad algorithms textbooks, and here's a representative one by Schiena. And all of them have this preface which says, okay, what is an algorithm? Well, algorithms are the ideas behind computer programs, okay? And here's the next one. An algorithmic problem is specified by describing the set of instances it must work on and what desired properties the outputs must have. So like sorting, right? There's a bunch of numbers. There's a definition of what a sorted order is, and that's what you're shooting for. And the conceptual hurdle for theory in machine learning is that machine learning procedures often fail this definition. Problem instances and desired outputs have no clean mathematical description. So you see here a tension between the traditional logic math tradition of theoretical CS, which is where this definition of an algorithm came from, versus these modern machine learning techniques, which in the traditional theory would be termed as heuristics. So here's an illustration using a representative machine learning task that is solved routinely today. So the input to this task is pictures that were labeled cat or dog by people. So that's the training data. And now a picture is just a vector of pixels, and the label dog is treated as 0 and cat as 1. And the goal is to learn a method to determine proper label, 0, 1, given pixels in a new cat or dog image, which was previously unseen. What's called generalization. It has to generalize to new images. So you learn this, this multi-layer net where pixels come in and 0, 1s come out. And we'll get into the training and what goes on in training in a bit, but let's just see what the input behavior is. F is a partial function. It only is guaranteed to work well on certain admissible inputs, which is cat and dog pictures. If it's fed a picture of you or me, we don't know what it'll output. You know, this F actually has not binary output, but it's a continuous output, so it could output other things. Now, notice that there's no mathematical description for what an admissible input is, because an admissible input is a cat or a dog picture, and we have no mathematical description of what that involves. And the best description we have today is these learned deep nets themselves. So there's no a priori description of what the computational problem was. And remember, F needs to do well on new images, which is not even part of the input on which the algorithm is being run. So of course, machine learning theory has developed concepts for this, but in terms of relating it to classical theory, this is the conceptual hurdle. And so if we lack mathematical description of admissible inputs and desired outputs, how do we know F is correct? And the key assumption is that the data consists of IID samples, independent identically distributed samples from some distribution of cat and dog pictures. And we are going to reserve some samples as test data or held out data, which are not used during training. And then at the end of the training, we test it on the held out data, and concentration bounds say that performance, say it's 95% accurate on test data, means roughly it's 94 to 96% accurate on the full distribution. Okay. By the way, this is a standard canonical model of machine learning where data is IID samples from some distribution. There are also ways of learning with data that's not IID, and that's an active area of research. So the secret sauce of machine learning and much of data science is that you write an objective L of theta that captures the problem. And the desired solution, deep net, language model, whatever, is trying to minimize this objective. So this objective is a loss, actually. And you minimization in quotes via gradient descent, which is this algorithm where you have some parameters for the net, and you're always, at every step you compute the gradient of the loss with respect to the parameters, and you take a little step determined by the step size eta in the direction of the negative gradient. So you're trying to reduce the loss locally. So for example, a simple loss function could be least square loss. So there's a desired output yi, and there's an output that the net is producing, and you minimize the square of differences between the desired output and the net output over the training data. Now, the reason I put minimization in quotes is that this simplistic gradient descent is not known to minimize the loss function, because this loss function is in general non-convex. So here, this loss is a function of just two parameters, theta 1 and theta 2 for visualization. And the z-axis is the loss function. And non-convex means that there's these hills and valleys. And minimization would involve going to the lowest valley. Now, of course, you can see in this picture that depending on where you start and what trajectory you take, you end up in different valleys. So unclear why this gradient descent works so well in so many settings. And it works well, meaning it makes the loss almost zero. And this minimization is NP hard for non-convex functions. Non-convex being this picture. There are hills and valleys. Now that's just with respect to making the loss zero on the training data. Of course, in deep learning and in machine learning in general, we are interested in loss or classification performance on the held out data, the test data, which is not used in the training at all. So it's even less clear why this method, which works only on training data, works on, and also does well on test data. So we'll return to that point as well. But that's the secret sauce. There are many variants of gradient descent, which this talk will not cover for simplicity. So with that picture, here are the 4 control knobs of deep learning today, on which there's a lot of work. So there's architecture, training objective, training algorithm, and training data set. So all of these have a profound impact on deep learning, and over the last decade, especially, there's been a lot of progress in figuring out this landscape and coming up with good solutions. And this work has been driven by intuitions, but theory is still lagging. And today's main point is that this simplistic black box view, although it's been very, very successful, may not suffice for getting us to where we want to go in AI or in sigmetrics. That is for designing flexible, reliable learners, where you have some kind of confidence of about how they work in somewhat new settings, for instance. So if you really want to have some confidence in how these paradigms work, like the deep learning paradigm, you have to understand properties of the net. And in this part of the talk, I'll give you some examples to show that architecture plus data set plus objective, etc., don't suffice to determine behavior of the trained deep model. You need to look at the dynamics of the training algorithm. So we'll have a couple of vignettes from theory and some takeaways. So the first vignette is a very simple model, gradient descent on linear nets, which sounds sort of nonsensical because the whole point of deep learning is that you have non-linearities in the deep net. But let's even understand gradient descent on linear nets. And the takeaway here will be that the objective looks nonsensical. You'll see that. It's not just that it's linear, but it even seems nonsensical. But gradient descent over-delivers by picking meaningful solutions. And it's better than the classical hand design algorithm. So I think this aspect, that it's better than the classical hand design algorithm, I think this aspect may be very relevant for the types of problems that are handled in sigmetrics. Okay, so this is the matrix completion problem, which maybe those of us who are old enough to remember the old Netflix when it would ship you DVDs weekly will remember this matrix completion problem. So the Netflix company at the time used to ship DVDs to users, and so it was shipping one DVD at a time. So it really wanted to get accurately what the users wanted so that it could suggest good movies to them. And so it had this matrix, which is the users time movies matrix. And every user has rated some movies. So this matrix has many unknown entries that are the question marks. And the hypothesis is that this matrix of preferences, the ratings by users of the movies, ratings on a 1 to 5 scale, is low rank. And I won't go into that assumption, but that's empirically true. And entries are revealed in a random subset of locations. That was the assumption. Users have seen some random subset of movies and rated them. And the goal is to recover the ground truth matrix. And the classical algorithm proposed by Sebro et al. And then analyzed by many other famous papers as well, was to find the matrix with best least squares fit and the smallest nuclear norm. The nuclear norm is the sum of singular values of the matrix. So that's the objective. So you're trying to find this matrix M, and you are minimizing the least square differences to the known entries. And then overall, you have this regularizer. Lambda is some constant that you can tweak times the sum of the singular values. So that's a convex surrogate for rank. And this convex is important because this whole objective is now a convex function. And so gradient descent will converge to some optimum solution. So this was a paradigm back in 2005. You would write a convex relaxation by thinking about the problem, you solve it by gradient descent or some variant. And then, as in this Candace Rec paper, you show that this is statistically optimal. And again, I have quotes here, and you'll see in a second why I have the quotes. Okay, so it was proven to be statistically optimal. So now in the modern deep learning era, as theorists started trying to understand deep nets, Gunasekar et al., the TTI Chicago group, suggested a new variant for matrix completion, which I'm sure people had tried before, but never analyzed. So find the matrix W as a product of two matrices. So you're trying to find so I changed the M to W, sorry. So you're trying to find an unknown matrix W. And you're just going to write it as a product of two matrices. Now, of course, we know the matrix is low rank, so it's a product of two low rank matrices, but you just write it as a product of any two matrices. Okay, and you're minimizing the sum of squares differences to the known entries. Now there are infinitely many solutions. Of course, every matrix can be written as a product of two matrices. And so basically, there's no constraint on the set of matrices that you're finding at all. And so there are many solutions, and the typical solution is nonsensical. But the empirical finding of Gunasekar et al. Was that gradient descent or backprop on this linear net, it's a linear net because there are no nonlinearities, it's just two fully connected layers. Gradient descent or this backprop algorithm finds solutions as good as the nuclear norm minimization. So that's what they showed in the experiments. And then they were trying to analyze this, but didn't have much analysis. So we, in this paper with postdoc Nadav Cohen and students Luo and Wu, we found we suggested a deep linear net for matrix completion, which is even more crazy. You're trying to find an unknown matrix. Instead of writing it as a product of two matrices, you're going to write it as a product of n matrices. So it's a depth n linear net, no regularization. It's an even less constrained parametrization, because every matrix is certainly a product of n matrices. There are lots of solutions, but we find empirically that gradient descent finds solutions better than the nuclear norm minimization in practice. Now, you may think, wait, it was proven to be optimal. Well, it's optimal with some theory constants and some theory terms like log terms and so on. And actually, it's better. So by a significant amount in practice. So once we discovered this phenomenon, we try to do mathematical analysis of this trajectory. And in this first paper, some students of mine have done a more complete characterization as greedy low rank running in a subsequent paper. So I won't really have time to describe this mathematical analysis in any detail, but I'll give you a flavor of it. So you're trying to find this matrix that's a product of n matrices, which you're thinking of as a deep net, deep linear net. So you analyze gradient descent, which is continuous time gradient, gradient flow, which is continuous time gradient descent. And you can start writing the differential equation that describes that evolution. And you're interested in the evolution of the product of these n matrices. So gradient descent is working on all of these n matrices, the parameters are the n matrices. And you're interested in the product of them, which is the end-to-end function that you're computing. So you can write down a differential equation that describes the evolution of that end-to-end matrix over time. So not just of the matrix, but also of its singular values and singular vectors. And you can show that the signed singular values of this product matrices have a certain evolution equation, which is like this. Now, I don't expect you to take it all in, but it uses a singular values, singular vectors. But the phenomenon I want to highlight is this rich get richer phenomenon. So sigma r is the rth singular value, sigma 1 being the largest. And you see that because there's this 1 minus 1 over n, when n is bigger than 2, this promotes low rank. So so initially the singular value, it's you start with a random initialization, singular values have no structure. If by just random chance one singular value gets a little bit bigger, it grows faster than the others. And so you stare at this and you realize that the goal of GD, if you can call it that, is to make singular vectors of W align with those of the gradient of the loss, and the singular directions grow one by one, according to this rich get richer phenomenon. And you see that there's a big difference between depth 2 and depth 3. So with depth 2, the singular values sort of all grow together. With depth 3 and higher, it's a very different dynamics, where the top singular value grows first and grows as much as it can. Then the second singular value starts growing, and then the third, and so on. So the process shoots up these singular values separately. Okay, I'll just pause in case there are any questions. No questions? Okay, carrying on. So next vignette in this power of the trajectory.
So there's actually one question from the audience. Let me. Okay, so I think Fernando, you can talk now if you unmute yourself.
Thank you. Very quick. What's the sign singular value?
What's the sign?
Sign singular values you mentioned there. Is it not the regular singular value?
Oh yeah. So yeah, this is just sign meaning we're using the sign. This differential equation. Sigma r is a sign. It has a sign.
Okay.
As you.
Okay.
Okay, next vignette is training of infinitely wide deep net set. And here the takeaway is that the architecture looks vacuous, but gradient descent picks a meaningful solution out of infinitely many possibilities. And there are various motivations from a mathematical viewpoint. It's the thermodynamic limit and the Gaussian process view of deep learning. Okay, let me first say why we are studying infinitely wide or infinitely big deep nets. So there's an overfitting mystery in deep learning. So remember overfitting. So that in introductory courses, we say, okay, here's data, and you're trying to fit a plot to this data. So you want the plot on the left, which is simple, not this complicated plot that's making all these wiggles to fit the data. And this is Occam's razor that overcomplicated models with lots of parameters, namely these squiggles, overfit and will not generalize to explain new data. Classical intuition, 1,000 years old. Well, in deep learning, that seems to be suspended. Overparameterized nets seem to do better than smaller nets when they're capable of fitting random data. So they're so overparameterized that it can fit even random data, random vectors and labels. Those nets have enough parameters to fit that, which clearly seems nonsensical. And nevertheless, when you fit these highly overparameterized nets on sensible data, even small data sets, they perform really well. So the mystery here is not the overfitting mystery, but the no overfitting mystery. So theory has been trying to understand that, and I would say it's still only partially explained. But here was a model that people came up with. And I'll illustrate this infinite net model by an example. Suppose the data set is this classical UCI data set, multi-class problem, 17-dimensional input, you're trying to predict properties of a tumor, and the number of training samples is 339. So this is from like 2 decades ago when machine learning used to look at these simpler problems. We're going to throw modern deep learning at it, train a fully connected 5-layer net on it. Turns out 5-layer net is not too bad. Okay, so it's something like this. Input comes in, output comes out at the other end. Now we're going to change this picture. We're going to make these internal layers infinitely wide, which means we're going to keep the input and output layer fixed. So it's still using the same inputs and producing similar outputs. But we're going to allow the width of the inner layers to go to infinity. So this is a mathematical limit, and you can study this limit. And what does it mean to allow the width to go to infinity? Well, there is a scale of initialization that still makes sense. And the scale we are interested in is where the expected node value is roughly equal at all layers in magnitude. So you look at this, okay, so now the internal layers are blowing to infinity. And those of you who know anything about the representative theorem of deep nets will say, well, this is too expressive. We see in introductory deep learning courses, neural nets courses, that even arbitrarily wide two-layer nets can represent every finite function. So the number of zero loss solutions with this 339 training samples is definitely going to infinity. Plus, why are we studying this anyway? It's infeasible to train. Right? How will we even verify any theory? Well, it turns out it's feasible to train. You can compute the number, the accuracy out of it. And that test accuracy on this data set was 51.5. And for random forest and Gaussian kernel, which is the traditional method, it was lower. So actually, these infinite nets do pretty well on these classic small data tests. So that was a paper of ours. So now having explained what these infinite limits are, let me tell you the motivation, the mathematical motivation. So one motivation is thermodynamic limits, which was this notion from physics in the 19th century, like Boltzmann and Maxwell, trying to understand properties of gases and fluids. And there was the molecular theory of gases, that particles are moving around, bouncing around, colliding with each other. And that's a discrete process, but the number of particles becomes large, so they took the infinite limit. And the infinite limit, this distribution of velocities, which is time varying, jiggling over time, you can treat it as a fixed distribution, a continuous distribution. And then that fixed distribution you can characterize using calculus of variations and physical laws, conservation, and so on. And you get, with these two geniuses, some mathematical understanding of this distribution and related to macroscopic properties of gases. So a similar infinite limit can be taken, a continuous limit, which happens to be correct. So in the sense that, okay, I'll give the details now. So there's a fully connected net. And so the net is described using this layers and nonlinearities in the usual way. And the WIs are matrices of the different layers. And here you're using the square loss between the net output and the desired output. And you're trying to understand the dynamics of gradient descent, continuous gradient descent. And you can express it as follows. The output, the derivative of the output vector is given as this, where H is this matrix, whose ijth entry is the product of two Jacobians. Sorry, the product of two gradients. It involves the definition of this matrix involves the Jacobians. And Jacob et al. Plus follow-up papers have analyzed this kind of dynamics. And the typical result is that as the width goes to infinity, you take the limit. This H matrix converges to some fixed matrix H star. And if you look at this trajectory, it's basically trajectory of least square regression with respect to a kernel matrix. And this kernel matrix is H star. So there's some classic algorithm, least square regression with respect to a kernel matrix. But there's a new kernel, this neural tangent kernel. And by the way, this infinitely wide net is definable in multiple ways and not all reduced to this NTK regression, neural tangent kernel. And people are still studying those infinite models. So I'll just briefly unpack the previous slide. So kernel regression is this idea that you can have an infinite dimensional representation of the input, phi of x, in a reproducing kernel Hilbert space. And you can do all the normal machine learning, the classical machine learning like SVMs, etc., if you can compute the inner product of the representations of two inputs. So phi of x is infinite dimensional, and you can compute the inner product in some compact way. So neural tangent kernel is this new kernel where this representation is infinite dimensional, and the corresponding entry for each parameter in the net is a partial derivative of the output with respect to this parameter at time t equals 0. So that's this infinite representation of the input that comes out of this. And so to do regression with respect to this kernel, you only need an algorithm to compute inner products, and you can do it via dynamic programming. So that was the first part of the talk. The second part is another vignette studying mode collapse in generative adversarial nets, GANs. And the story here will be that here the training objective delivers less than you expect. And so caution is warranted in multi-objective multiplayer settings. By the way, I forgot to take questions. Any questions, Longbow?
No, I think we're good.
Okay, thank you. So this generative adversarial nets is, well, I have this picture from MIT Tech Review where they drew it as a duel between two players, and that's the idea. They call it dueling AIs. So the background for this is deep generative models. For instance, there are models called variational autoencoders that have been studied for much longer, where the idea is that you have a deep net or some model where the input is white noise, Gaussian, and the output is some very structured input like an image. But it's been used, this idea has been used for scientific applications where you're trying to generate representative physics experiments or things like that as well. So this training, how does it work? You're trying to maximize the log likelihood objective. So this model is transforming white noise, the distribution you understand, to this complicated distribution. And if you can compute the probability of this image, you can do training via backprop to maximize the expectation of the log likelihood. Okay, so this model, the trained model, is transforming the Gaussian distribution to some complicated distribution on real life images, say images of faces or whatever, or outcomes of physics experiments. So the implicit assumption here is that this real life distribution of interest is generatable in some sense or approximable by a deep net of reasonable size. Now, generative adversarial nets were invented by Goodfellow et al., a very major paper in the field. And the motivation was to avoid log likelihood objective because it favors outputting fuzzy images. Because this log likelihood cannot bear to give zero probability anywhere because log of 0 goes to infinity, and so minus infinity. And so it tries to give probability everywhere, and then it comes up with these fuzzy images. So instead of log likelihood, you use the power of discriminative deep learning, that is classification problems, to improve the generative model. So we know that deep nets are very good at discriminating cats versus dogs or A versus B, etc. So you use that power to improve the generative model. So as I indicated earlier, there are two nets here, not one net, and they're fighting against each other, dueling. And there's a discriminator net and a generator net. The generator net is training to learn to produce synthetic images that are good, that look like real images. The discriminator is a net that's being trained to distinguish between these two types of images, real and synthetic or fake. And so they each have their trainable parameters in there. So the discriminator is being trained as follows, cats versus dogs again. Cats is real images, dogs is synthetic images. It's being just trained to output 1 on real images and 0 on synthetic images. So formally, there's kind of training of two nets, which are opposing each other in some sense. The generator is being trained to fool this deep net, obviously. So it's trying to produce synthetic images that look like real images. So the generator outputs 1 on them. So they're dueling against each other. So formally, the objective is a min-max objective that I think in sigmetrics, you know from game theory. And so there's minimization over one net and maximization over the discriminator net. The discriminator net is trying to maximize the probability of discriminating between the two distributions, and generator is trying to make it minimize that probability. So formally, what I've described here is a later model called Wasserstein GAN by Arjovsky et al. And there are many variants of this GAN idea. So what's a win for the generator here? If the objective becomes 0, namely the discriminator is not able to distinguish between the two distributions. Now in practice, the objective doesn't get 0, it gets small. But the point is that you want to get towards that, and further training of the discriminator doesn't help. So that's an equilibrium of some sort. So that again is a concept very familiar to sigmetrics audiences. So that's an equilibrium you'd like to have. And in that equilibrium, at least the discriminator is not able to discriminate between the two distributions. And the question is, how good is that distribution? So after several many years of tweaking, now GANs actually produce very good looking images. What I had earlier was actually a GAN produced image. So the quality looks good to the human eye. But underneath, what can spoil a GAN, or a GAN trainer say, is mode collapse. Namely, that the discriminator learns to produce good-looking images, but there isn't a lot of diversity. And the traditional way of thinking about this lack of diversity is that since the discriminator only learns from a few samples, 100,000, a million samples, whatever, it may be unable to teach the generator to produce distributions with sufficiently large diversity. And people came up with many ad hoc qualitative checks for mode collapse. So what we came up with a couple of years ago was a new theory. And the new insight was that people are thinking about the wrong problem. The problem is not with the number of training samples, although of course it's good to have more training samples, but the size or capacity, representative capacity of the discriminator. Specifically, what we showed with Ge, Liang, Ma, and Zhang was that if the discriminator size is n, and I won't quantify that size because it's different from number of parameters, then there exists a generator, which is not much larger, that generates a distribution supported on n log n images, so not much more than the discriminator size, and still wins against all possible discriminators of this size. And now tweaking the objectives or increasing the training set doesn't help. It's not a property of the training set or the particular objective. Because I mentioned there are many GAN objectives. And this suggests mode collapse because, of course, presumably the real life distribution has infinite support. There's infinite diversity there, like real life images or something. And this is saying that, n is discriminator size, its capacity, maybe it's in millions. So, there's a limit on the diversity of the set of images based on the discriminator size. So what this theorem says is that smaller discriminators are inherently incapable of detecting mode collapse. Now I won't do the proof sketch, but it's an epsilon net arguments, and those of you who know epsilon nets can probably read this and understand. So what was the takeaway? So theory suggested that GAN's training objective is not guaranteed to avoid mode collapse. So it looks, the objective you train, and if the objective is close to 0, everything looks good, but that's not guaranteed to avoid mode collapse. And it's kind of a new notion of generalization in this setting. It's not the traditional notion of generalization. And here, if you're interested in mode collapse, you cannot avoid it. So when we published this, and people, especially practitioners, started asking fine, it's good theory, but what happens in real life training? Can you detect mode collapse? So we started thinking about that. How to detect support size of the generated distribution? And we thought of the birthday paradox test. You see, the problem is that, you know, there might not be a lot of modes, but it could still be hundreds of thousands or millions of nodes. So some human would have to sit there and look at the output of the GANs, which is in the millions, to detect mode collapse, whether it's, you know, repeating the images. But then we realized there's a birthday paradox, and maybe many of you have seen this in discrete mathematics, that if you put 23 random people in a room, and this is a good trick to pull in your small classes, the chances at least to have the two of them share a birthday. It's called a paradox because you would naively imagine that you need to put 366 people in a room to, or something like that, to have a high chance of a collision in the birthdays. And the asymptotic statement is that if you have a distribution supported on about n images, then the probability a sample of size square root n has a duplicate image is pretty large. So we're going to flip this. We're going to look at small samples of size square root n, you know, assuming you have some suspicion that the true size of the distribution is n, it's supported on n images. We're going to look at a small sample of size square root n and look for duplicate images. So that's the birthday paradox test. Take a sample of size s and look for near duplicate images in there. And if you see near duplicate images with probability at least a half, then heuristically the distribution only has about s squared distinct images. You know, there's some asterisk here, you can make this more precise, but let's continue with this informal statement. So what is S? So, you know, let's say you think the distribution has only 1 million distinct images, you would look at a sample of size 1,000, which is still arguably a little bit large for grad students to work through. Now on this sample of size 1,000, you can do first a heuristic pass by a tester, automated tester, which flags suspected duplicated images. And then the human grad student will look at the 10 or 20 most likely collisions and verify that they're actually the same image. So that's the method, that you use a heuristic test to flag possible near duplicates, and the human in the loop will verify the duplicates. So when the human in the loop says they're duplicates, they're actually duplicates. So we ran this on various well-known GANs on popular data sets, and this was from 2017, but people have done similar experiments in subsequent years, and it still happens. So like DC GAN, the duplicates suggested the support size was 250,000 among human faces. And for BioGAN, it was about 1 million. And there are similar results on CFAR10, and follow-up work has confirmed lack of diversity. We actually saw this even in the latest GANs, actually. We tested it recently. So that was about a setting where there's GANs where you have an interesting new way of doing deep learning with this dueling deep nets. And the objective doesn't quite reflect what's going on underneath. So you need a theory to understand the limitations of this model. Any questions?
So there is actually one question from Zhenhua Liu. So Zhenhua, please go ahead.
Yes. Maybe I missed something, but this result is very insightful. Is there any suggestion how to solve the issue of the collapse?
No. So what this theorem says is that there's always a near equilibrium of this type with mode collapse. And this result is not taking into account training. So indeed, as I've been emphasizing all along, we need to look inside the black box of the training. So this result is in the black box model where, you know, there's an objective, and basically you can find any deep net that you like, and then there exist deep nets which will cause mode collapse. And there's an equilibrium, in fact, an equilibrium of deep nets where mode collapse happens. Now, to solve this problem, you would have to somehow modify training and look at the dynamics of the training.
Okay, thank you.
So there is actually one more question from the audience. So let me allow to talk. All right, so I think you can unmute yourself and talk. Hello, Isaac? Okay.
Continue on. Okay. So why does training on task A? So this is the part 3. Why does training on task A help later with solving task B? Which is something that humans do all the time, right? You do something like, say, major in mathematics, and you pick up some skills, and those help you later for doing something else, like doing well in law school or finance. So there's this notion of learned skills, and we want the formalization of that. And just to emphasize why this is different from the canonical machine learning framework, the most canonical machine learning framework, where it's assumed that data points come from a distribution D, and S is a set of training data points, and you train the model by minimizing some loss function on this training data set. And learning works if this loss function is similar on the full, the training loss is similar to the test loss, so namely the loss on the full distribution. So the important thing here is in this canonical framework is that there is some notion of learning, measured by loss, performance, and you want the performance to be, and this performance is the same on training versus test data, and that's what you're measuring. But here we are interested in training on task A and then doing well on task B. So test task is going to be different from the training task. And so therefore we must look for learned skills inside the trained model W star. And then use that trained model W star for some other task, possibly by modifying it a little bit, tweaking it a little bit. This is an important paradigm lately, and the theory for this is rather sparse. So let me give you an example of this kind of learning using language models. And these are language models like GPT-3, which are massive, trained with very massive amounts of text. And they've revolutionized natural language processing. So these models are just trained to solve fill-in-the-blank tasks. So for instance, given a partial sentence, Rob went to the cafe and ordered a blank. The model, it takes these words and has to give a distribution on the next word. So for instance, it might say the probability of latte is 0.15, probability of a Danish is 0.1, but probability of dog is 0.0001, because usually you don't buy a dog at a cafe. So it comes up with this probability distribution on the next word. And the training objective is a log likelihood objective, where you're trying to maximize the probability of the word that actually appeared in the corpus. The corpus was used to generate this fill-in-the-blank task. So there was a ground truth word here. And over the entire corpus, you're trying to train the model to produce the correct word with good probability. So as I mentioned, these models are massive. They're so massive that you can't even train them in most academic environments. But once the model is trained, you can use it and tweak it for other tasks. So that's the paradigm. That this internal representation of the text of a pre-trained model turn out to be useful with no further fine-tuning or maybe very small fine-tuning for lots of other language tasks. So this is an example of training on task A, this fill-in-the-blank task, and then later using that learned representation to do well on task B. And there's very little theory for this kind of learning. Is it something special about language modeling itself? This objective, this log likelihood objective, or current deep architectures, or the training algorithms? So to answer these questions, we need to start looking inside this black box. So next few slides is some first cut take of this, a mathematical exploration of why language models help solve downstream tasks, with students Nikun Sonshi and Sadika Maladi. So we start with the observation that many classification tasks of interest, at least in the standard test beds, can be phrased as next word prediction. Here's a simple example, just for illustration. Sentiment classification. Given a movie review, you classify that as positive or negative, or maybe give a numerical score, how positive or negative it is. So of course, this is some kind of a language understanding task. But you can phrase it as a next word prediction as follows. You take the review, which is a bunch of text, and tack on this phrase, I think the movie was blank at the end of it. Now you can feed this text with the blank at the end into a language model. And intuitively, the sentiment ought to be apparent from the next word predictions of this model, like what it thinks, is it, how likely is good or amazing at there versus terrible or may. That gives you the idea of the sentiment of the review. So we start with this observation, that a natural task is one that's solvable via the linear classifier on this vector of probabilities that, say a human would give, P star. Now, of course, as the language models get good, they would approach this vector of human probabilities. And there's an empirical finding in the paper that this paradigm of reducing language tasks as next word prediction to next word prediction actually works for many tasks in the test beds. And in fact, it suffices for the classifiers to look at this next word probability for 10 to 20 keywords. And these keywords depend on the task, of course. So this fact that it's not just solvable via linear classifier, but it's solvable via sparse linear classifier, which only looks at 10 to 20 words. That's part of the definition of a natural task. So these are natural tasks. Now, given that these are the tasks we are interested in, we want to show that doing good language modeling, like being good at this next word prediction, will improve the quality of solving this task. And I'll just quickly go through this theory. Well, in a language model, the way the output is produced is that there's two things. So there's a representation of the text, f of s. S is the text context, called context. And to produce this distribution on next words, which is over all dictionary words, the distribution over all dictionary words, you have the so-called word embedding matrix, phi, which for every English word has a vector called the word embedding. So you take the matrix vector product of this word embedding matrix with this representation matrix for the text. So that gives you a new vector. And now on that, you produce a softmax. Sorry, I should have put a softmax is a way of converting a real vector using exponential activation to a distribution. Sorry, I should have put a formula for that. So given that that's the architecture of a language model, one can see what happens in an optimum model. So optimum just with respect to gradient descent. So the first optimality condition says that for a fixed phi, the best f star that minimizes, so this may not be the best period, but just best for this gradient descent, that minimizes this entropy objective, this log likelihood objective, satisfies some first order condition that the product of this phi times this matrix of, phi times this vector of ground truth probabilities from humans is equal to the probability that the model generates, the same product for the probability of the model produces. So it's this condition. And formally, it's just saying that it's guaranteed to learn this next word distribution only up to projection in the d-dimensional subspace spanned by the word embeddings. Now, the claim is that, it is a mathematical claim, that if phi respects synonym structure in the language, that a synonymous words have similar embeddings, which is a natural property for word embeddings, then these natural tasks continue to be solvable via P star S's that satisfies these subspace constraints. So remember, we have this notion of natural tasks. Those continue to be solvable. And then you can, using all these properties, show that improving the language model, namely the quality of the next word prediction, leads to better classification. So you have the logistic regression loss for the task that you're interested in, this classification task, which is natural. Tau is the measure of naturalness of the task, which I didn't formalize too much, just told you informally. And epsilon is the suboptimality of the training objective with respect to log likelihood. So notice that this theory, this simple theorem, is assuming something about the task, something about this phi that's respecting the synonym structure of the language. It's using something about the first order optimality condition of the language model. Now, of course, that's still a very static analysis, first order optimality. Ideally, what you would want to do is a dynamic analysis of the trajectory, and that we haven't done, and that's much harder. I have maybe in 30 seconds, I'll say there are other analyses we've done. So this is another way of doing this task A versus task B in language, where you use a text corpus, large text corpus, to train a deep representation function directly. So you don't try to do next word prediction, you do something else. This is called contrastive learning. So you're mapping a sentence or a piece of text like a paragraph to a representation vector. And the objective you have in mind is, for training, is that adjacent sentences are somehow similar to each other. And that's a property of text, that there's some semantic coherence between adjacent sentences. But if you take two random sentences from the corpus, they are unrelated. So this objective is some kind of smooth way of saying that adjacent sentences have high inner product, the embeddings have high inner product, and random pair of sentences have low inner product. If you think about how this log and exponential interact, that's what it's saying. And again, this is one of these things where you train embeddings using this kind of objective, and those embeddings turn out to be useful for later tasks. And this can also be done for images and many other kinds of data. So we have a paper that analyzes why this kind of learning works for downstream tasks. So again, you have to make some assumptions about the tasks and so on. So that gives you a taste of how theory can start to give some insight into many of these very interesting deep learning paradigms that have been invented in the last 5-10 years. So I'll finish, if I may, with some speculation that about flexible and reliable deep AI agents may need some new design principles. And this is where the field is going. Like from the Bengio group, there was this paper called Recurrent Independent Mechanisms. So inspired by the success of deep learning, now you have multiple deep nets inside your learner, and they're interacting in some flexible way, and the input comes in, and these mechanisms may be actually bidding in some sense on parts of inputs to work on. And there's a society of agents who are choosing through some attention mechanism to compete or collaborate, and there has to be some kind of a created assignment via some suitable gradients. There's some notion of training and so on. And my point is that this is now operating way beyond the traditional machine learning framework. Multi-objective, like you had in GANs in some sense, no fixed training distribution, etc. And I think here you need new theory and principles. I think the credit assignment, how to train, how to test, nothing is really specified. And so I'll end with this thought that there's a need for this new theory and principles in these new settings where we're trying to take machine learning and AI. And as we've seen a couple of times, machine learning relies on average performance on data drawn from a fixed distribution. And there are these proposed alternatives that I hinted at, like meta learning, Bayesian frameworks, etc., which are variants of distribution on distribution. So you may have distribution on task and then distribution on data or something like that. So there are these interesting models that deviate from the very simple paradigm, but if you step back, it's still, totals upon totals. So there's a total, which is what you're interested in, which rests upon some other total, like distribution on tasks, which may rest on some other things, distribution on experiences, whatever. But at the bottom, it's all resting on some independent samples, IID samples from a fixed distribution. And maybe that's okay, but it feels like that paradigm is insufficient to capture richness of everyday interactions, because it seems that low probability events are maybe an important test of flexible agents. And this is, again, maybe something that's of interest in sigmetrics. And conceivable, and when I say that, I'm not completely confident in this prediction, but because it's conceivable, and this has happened many times in the last decade, that things that looked not solvable by deep learning somehow became solvable when you increase the scale of the net or the data set or whatever enough, and just use enough effort. So yeah, so take that prediction with some grain of salt, but better understanding would always be helpful. So we're starting to opening the black box of deep learning. In some admittedly stylized settings, properties of trained models have proven to arise from a complicated interaction of architecture, objective, training algorithm, and data set. And formal understanding of these properties will be crucial for flexible, reliable AI agents. Thank you very much. And I have listed some resources, including my blog and Twitter feed here. Thank you very much.
Thank you, Professor Arora. So let's see, I think we have questions. Srikanth.
Hi, thanks for the great talk. I have a question on, so there's a lot of work on analyzing the impact of width on performance, but I guess I don't see too much work on the impact of depth. I know there's early work on realization theory. I mean, that if you want to approximate a function to a certain degree of accuracy, depth can help with reducing the number of neurons and so on. But this intersection of what you talked about of the algorithm as well as architecture and width has been studied, but not so much on depth. And depth seems to be very important in practice. I was just wondering if you can tell us a little bit about the state of the art there, whether you think it's not important, depth is not as important.
Oh, depth is very important.
Yeah, exactly. So why has it not been as well studied?
Okay. So by the way, I forgot to mention, forgot to point it out, but the deep matrix factorization, right?
You mentioned that, right?
Better, higher depth is better.
Correct.
So that's indeed an example. And there've been other such examples where you can analyze the effect of depth. But yeah, full analysis has been difficult in the nonlinear setting. Yeah, but definitely depth is very important.
So there is no such thing as like NTK or thermodynamic limit for...
No, there's no NTK. But one thing, so in order to go to high depth, something that seems very crucial is batch normalization schemes, or just some kind of normalization schemes. And there have been quite a few papers out of my group and now from some other groups understanding the dynamics of batch normalization. So that theory, I think, can work its way towards understanding the impact of depth. It gets very, very complicated. You're analyzing real life nets and dynamics there. So the kinds of theorems you prove are fairly limited, but they're already interesting. So I suggest looking at that.
Thank you.
Thanks. So I think there is another question from Zhenhua. Zhenhua, go ahead.
Yes, thanks a lot for this very insightful talk. I really enjoyed it. So as a junior researcher, and I think we also have graduate students, young faculty in the audience. So can you quickly give us some suggestion about how to do great research like yours?
So by the way, since you mentioned Tsinghua, probably many of the students I mentioned are Tsinghua students. So Tsinghua students already seem to know very well to do great research. Yeah, I think the important thing in theory of deep learning is to strike a balance between being able to say something and saying something interesting for the new settings. I think that's the interesting trade-off that has to be made. And just going by the amazing Tsinghua students I have in my group, I think the new kind of students that this field needs is those who can combine experimentation and mathematics. And yeah, whatever you're doing at Tsinghua, but at least many of them come from maybe the Andy Yao Institute. Yeah, they're amazing and they know those skills. And I think that's really an exciting difference from traditional theory, that I was used to. That these students do very good experiments, and they combine theory and experiments to gain insight, and then go back to proving some theorems to support the experiments, and back and forth.
All right, so let's see if we have any other questions from the audience. So if not, I actually have a question that I wanted to ask. And so you mentioned a few times during your talk that essentially, so architecture, data, or objectives, they're not enough. So in a sense, we need to look at the dynamics of the algorithms. But we often have this question in the algorithm design, or in particular when we design the deep reinforcement learning, the algorithms or mechanisms, we still need to specify all these architectures and also somehow treat the objective functions. Do you have any suggestions in terms of if I still need to deal with this? Is there some sort of a rule of thumb where I can basically apply and try to do that more efficiently?
So is there a takeaway for deep RL? I don't, I follow it, but I haven't thought too much about it. I mean, that, as you say, has an interaction of so many things.
Right.
The data, the experience,
right?
It's basically everything in deep learning has to be put in there. It starts getting complicated to give sort of concrete theoretical guidance there. In terms of, but if I interpret your question less ambitiously, what are some points where there are some interesting takeaways? So I think the dynamics of training, especially in these new nets, new families of nets which use normalization, I think that's very interesting. And theory has already shown how that can, many intuitions that people had there were incorrect, or propose new kinds of intuitions based on the analysis. So maybe it's still not quite shovel ready. You can't apply directly to something, but if you're interested in understanding deep learning, I think that's some place I recommend. But also some of these stylized models actually have had already have affected some practice. So for instance, this notion of with no nonlinearities and just multiple layers, you could have a very strong regularizer effect. The low rank that already has been used. I showed it to some of these experts, Lequin and Benjo and so on, and immediately this Lequin's group sort of applied it to a product, and it worked very well. So yeah, this can happen.
That's cool. So yeah, I think that has another question. So let's.
Sorry for another question. So since you mentioned the fluid model, this actually reminds me of the in the TCP part, when people model the PCP protocol, they also do from a discretized system, but they use the control theory and the dynamic system to do that. So which I think has some similarity with what you described in the first part of your talk, right? Can you quickly comment on that one? It is the right understanding?
Yes, but in TCP, I guess there is the game theoretic angle. But yeah, I mean, in general, it's a paradigm in a lot of mathematics that you go from discrete to continuous, get insight, and it's indeed doing that. If that's what you mean by the.
Yeah, because I think the exciting part for me is for TCP is the model, the dynamic control model is used to explain the distributed control in TCP. Right. And here, the distributed learning.
Completely analogous, yes.
Right, so I think this might be very exciting.
Yeah.
Okay, great, thank you.
Okay, so there's one more question from the audience. Let's probably just take that. Vijay.
Thanks, Longbo. Thanks, Longbo. Sanjeev, thank you very much for an excellent talk. I very much enjoyed it. I had a quick question, which was along the theme that you were mentioning. It's not just the architecture and various things, but the dynamics of the algorithm. So which means if you change the algorithm, you should get a different solution, perhaps. And is there work on that? Or, I mean, there's some nice thing with gradient descent, but suppose there are more, you could conceive of other algorithms. Would you be able to shed some light on that?
Yeah, so yeah, I didn't get a chance to cover that. So that's the emerging theory of implicit bias. It's called implicit bias of the training algorithm. And that TTI group I started with on matrix completion came out of that work. So it's been done in fairly simple models, but you know, even for logistic regression, you know, simple models, it's been shown that the training algorithm has an impact on what kind of solutions is picked, you know, when there are multiple solutions. So that's, yeah, the buzzword you should look for is implicit bias of gradient descent or of the training algorithm. And there's a little field of papers in there in the last 4 or 5 years, including from my group, but also many other groups.
Thank you.
Thanks. So I guess there have been a lot of questions. So I guess in the interest of time, so we thank Professor Sanjeev Arora again for delivering this wonderful, inspiring talk. And thank you very much.
Thank you.
Also, I'd like to thank all the audience for attending the keynote and the Achievement Award talk by Srikanth. And so I suppose this concludes our morning session. And so there will be a break and we will be back at 1:30. Thank you, Professor.
So can I sign off or?
Yeah, I think now it's done.
Okay.
All right.
Thank
so
you.
See you later.
Thanks. Bye-bye.
Thanks. Bye.